Give them their money back on the video. How about that?
The subscription they pay.
Yeah. So an expression tree for this, and there were two ways to interpret this, a plus b minus c, depending on how you define the precedence. If you go straight left to right, there's a plus b, and here's c, and subtract c from a plus b, but there was other ways to do this also. And over here, 2 and y get multiplied, and then x and this get added, and then these two things get multiplied. So that was the most popular expression tree for this. When you parse this in post order, so left, right, node, start at the root, move left, 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 leftmost one is A, go up, come down to the right, B, and then visit the node plus. So this is postfix order. Visit the right is C, and then the node is minus. And then before we print out the star, we have to traverse the right subtree. So do the same thing over here. Visit this node, come over to the left, X, and then traverse this subtree, left, right node, so that's 2y times, and then come up to the root is plus, and then finally come up to the root of the whole tree, which is times. And that's postfix, and you can evaluate this with a stack by just pushing things on the stack, pop them off, operate push when you hit an expression. So that's the LRN traversal. Undirected graph from the adjacency matrix, I think everybody nailed that. Except one case where there was an extra edge for some reason. But yeah, it just comes out if you did your matrix A, B, C, D, E. It just comes out like that.
That's prettier than what I had.
Yeah, me too. The first time I did it, it was all over the place, but when I did my key, it like came out nice. So, and there's 6 edges. You can just count them up. And the degree of each vertex, all of these have degree 2 except for E, which has degree 4. A number of people added 4 plus 4 2's and divided by 2 and got 6. So that was nice to see. It's a good check to make sure that you counted everything correctly. True, false. Dijkstra's algorithm is used to find a minimal spanning tree. That's not true. Right? We talked about Prim's algorithm for a minimal spanning tree. A spanning tree is looking for a tree within a graph that has the lowest total cost. Okay, Dijkstra's algorithm is looking for the shortest path from one point to another. Those are separate things. Prim's algorithm is a good example of a greedy algorithm because it finds the cheapest branch to add on to its tree at each point. In a binary search tree, each node is greater than or equal to every node in its left subtree. A couple of people said false, but said it's because it should be greater than, not greater than or equal to. So I give you credit for that, but technically it could be greater than or equal to.
I got that backwards.
So I was actually wondering about that. I don't know if I'm saying true, but so if you have 2 equal things in a binary search tree, how do you decide what to do with it?
That's a good question. I don't know if there's a standard answer for that.
Because I mean, if you get 1, 2, 4, 4, 4, right?
Yeah.
How do you parse those 4s? Like, how do you decide?
I mean, you could perhaps do it like, so here's 1, 2, 4. I don't know. I mean,
yeah, I mean,
you could do that. It would be a little weird.
Down the middle, make it a ternary search tree.
Wouldn't you want to make it depend on how it would print out in order traversal?
Yeah, well, this would still print in the correct order.
Yeah. It's just a weird thing to think about.
Yeah, it is, and I've never encountered a case where we do this, because usually if you're storing data in a tree, you're either storing just the data itself, or you're using it as an index into something else.
Right.
But if you were storing grades and you wanted to be able to count them or something like that, you might do it like this.
Yeah, I think it depends on the circumstance.
Yeah,
Yeah.
but it probably wouldn't
Sometimes
be
you can just
optimal.
replace it or just do nothing.
Or increment a
Sometimes
counter.
you can add
Yeah.
Or something, yeah.
So you might have a counter associated with each one if you actually cared about how many 4s you got.
Right. Okay.
So I didn't mean that to be subtle, so people who were tripped up by that, I gave. Every graph contains an Euler circuit? Absolutely not, right? You got to have 2 or fewer vertices with odd degree, or no vertices with an odd degree for a circuit. For an Euler path, you need 2 or fewer, so no, not every graph contains an Euler path. Binary search trees are always balanced. That would be nice, because we never have to talk about balancing, but that's not true. A binary search tree can be searched recursively, definitely. Right? Everything can be done recursively almost.
Just different levels of effectiveness.
Yeah. Now, if we had a recursive algorithm for cooking bacon, we'd have like a unified theory of everything.
It would be really inefficient though.
Yes.
You have to probably cook each molecule or something stupid
Yeah.
like that.
Or cook bacon that somehow can cook other bacon.
Yeah.
Something.
there you go.
Well,
There you go.
Isn't it to make an apple pie, you must first create the universe? So,
Yeah.
so to cook bacon, you must first create the
Right.
universe.
If you use bacon grease to cook your bacon.
Yeah,
That's
yeah,
true.
perfect. There you go.
That's not bacon, that's like an element of bacon, that's an element of the set bacon.
Yeah.
So,
So
it's like
bacon-
it's creating a child process to
So
make
bacon, porking into bacon. Porking? There we go.
All right. In a binary tree, every node has 2 children. No, every node has 2 or fewer children, but you don't have to have every node being complete like that. Balanced tree of height n has exactly 2 to the n nodes, not necessarily. Right? The lowest level can actually be.
Because of the same reason we just pointed out, basically.
Right. That is still balanced, even though we're missing, in some sense, that last node. But it'll satisfy our recursive balance definition. Balanced tree must have balanced left and right children. If they exist, this is true. And if they don't exist, they're technically balanced because an empty tree is balanced also. Post-order traversal will visit the nodes in sorted order. No, that's an in order. In order, get it in the right order. A binary tree is also a graph. That is true. Okay, a graph is just a collection of vertices and edges with a few properties. Binary trees are just one example of that. Search time for a node in a binary search tree is related to the depth, absolutely. That's why we care about balance. Basically, the time it takes you to get to a node is related to how deep it is in the tree. So that definitely affects the search time. And the maximum depth for a binary search tree with n nodes is log of n. That's only true if it's balanced. All right, here's a perfectly good binary search tree. And its height is much bigger than the log of 6.
Will the final be weighted towards content that we learned after this, so literally just formal languages?
No.
No. Okay.
Won't be a whole lot of formal languages on the final because we haven't had a chance to do quizzes and such with that. But it will be probably weighted more post-midterm, maybe. So do we want to talk about material for the final?
Yes, we.
Yeah? Everything? Any questions?
What's on it?
Let's personally go through the topics.
I feel like we could find a more efficient way of doing that, right?
Yes, I
Because that
know.
would literally be just doing the whole course over.
Yeah.
It would be good for you though.
It would be. Let's see, so I think we started with set theory. So collections of objects, set operations, unions, intersections, complements. Complements tend to trip people up, but A take away B, which is sometimes written A minus B. It's the things that are in here but not in here. Okay, it's A with anything that happens to be in B removed. Okay, if there's things in B that aren't in A, that's fine. But if you find something in B, take it out of A if it's in there. So it's a complement. And in the case where A is our universal sense set, so universe, take away A, that's our usual notion of a complement. It's everything that's not in A. So as long as you know what the superset is, it's all the other stuff. And that we sometimes just think of as a complement. Let's see, subsets, equality of sets, yes?
Could we go over the power set again?
Yes, power set is the collection of all subsets. So if A equals, X, Y, and 1, then the power set is a set containing sets. It contains a set X, a set Y, a set 1, a set XY, a set X1, a set Y1, a set XY1, and the empty set. So all possible subsets.
Is A equal to X by 1 equal to B equal to YX1?
Mm-hmm. Yeah, this is the same thing as,
And we have two X's over there? Is that
no, don't write this. Right, so if you want A union A, just write this. Don't write elements twice.
But they are not so equal then, right? Those two sets are not equal, are they?
This and this?
Yes.
Technically, yes, but I don't even know if that's like valid to write, but I'm going to start saying it's not.
What was duplicate entries?
Is this like,
Say what?
With duplicate entries?
Yeah.
is this like a gray code with like a bit representing whether or not the,
So we can make a binary representation of a set,
okay.
right, of a subset. So for example, if we assign an ordering to these elements, we could make a string B2, B1, B0. And this is 1 means that 1 is contained in X, 0 means that it's not contained in X. And this bit, a 1 might mean that X is contained in, let me not call it X, let me call it A. Let me call it S for subset. Right, so if we order these elements of the set, we can define a subset as a binary string, where we have a 1 in a particular position indicating a particular element is or is not in that subset. So this would be for S a subset of A. And so if we have n elements in the set, we can use an n-bit string to represent any subset. And we know there's exactly 2 to the n n-bit strings. That tells us there's 2 to the n subsets. So our power set has 2 to the n elements for a set of n elements, as long as n is finite.
Speaking of infinite,
So there's these sets we talk about: integers, reals, complexes, and so on. Naturals, which sometimes are just positive, sometimes they include zeros. Pick 2, top 2. And we have ways of specifying, so even equals the set of all elements in Z such that that element is congruent to 0 mod 2. So we can use this kind of notation where we say such that. And sometimes it's a colon, sometimes it's a vertical bar. Other ways that we can specify sets is interval notation. Right, so these include the endpoints, these do not include the endpoints. So we can specify intervals like that. General note for the exam: if there's something on the exam you're not sure about, you're free to ask. Like if I ask you a question about these and you don't remember what the difference is between a bracket and a parenthesis, maybe that's what I'm testing you on, maybe it's not. Doesn't hurt to ask. Can you tell me what the difference is between a bracket and a parenthesis. If that's what I'm testing you on, I'll say I can't tell you that, you need to know it. But if I'm just using this as a way to create a problem about intersections, right, I'd be happy to tell you the bracket means it includes A, parentheses means it doesn't include B. So don't hesitate to like ask, don't run up every 5 seconds with it, but you know, if you're not sure, you can always ask. We drew Venn diagrams to picture things like intersection and union and so on. Subsets, right, everything in A must be contained in B. A proper subset, everything in A must be contained in B, but they can't be the same set. And not a subset, there's at least one thing in A that's not in B.
What's that second one? I don't remember.
That's a proper
Yeah.
subset.
I don't know that we discussed that ever, but that's an interesting concept.
Yeah, so everything is a subset of itself, right, trivially.
Yeah.
But if you're interested in the interesting subsets, right, let A be an interesting subset of B, we can say it's got to be a proper subset, which means it's not B itself. So there's at least one thing in B that's not in here.
Yeah, it's not a difficult concept to grasp, but I don't think we actually talked about
It's
that.
possible we didn't talk about it.
Yeah. Think that.
For a finite set, that's the number of elements in the set. For an infinite set, this is something different. It's the cardinality. And I won't go crazy on you with cardinality. But cardinality for an infinite set measures how big it is in the sense of, is there a one-to-one mapping between the elements here and the elements here? If there is, then they're the same size. If there's a one-to-one mapping from here to a subset of this, but this is somehow bigger, right, then this has a larger cardinality. And the main take-home message was, right, cardinality of the integers is what we call aleph naught. And this is what we call countable. It means we can put a one-to-one correspondence between consecutive integers and the elements of this set. So integers, even numbers, odd numbers, prime numbers, multiples of a trillion, these are all countable. Rational numbers are countable, but real numbers have a bigger cardinality. So we can't map integers to reals one-to-one. And then this links into 250, because they're set identities. So there's commutivity, there's associativity, there's distribution. And so on. And these look a lot like what we saw for ands and ors. And this basically becomes an or, and this becomes an and. And there's the De Morgans where we take complements and so on and so forth. So.
Will you be having us do proofs on the?
Sure.
Great.
Yeah, why not?
Yeah, I mean, if I had to pick like one thing that we went over, it would probably be proofs again, just more examples. Maybe tomorrow or something.
Well, we'll get to that next, actually.
Maybe a more general way of solving them.
Yeah, I mean,
Practice.
yeah. Nobody likes to answer that.
Yeah, I know. So we have identities. We can prove theorems about sets using these algebraic approaches, or we can use membership tables. And membership tables are like truth tables. So we can say if something is in A, then it's also in this, right? And so you can make a truth table and put ones and zeros for whether something's a member of a set or not. And it's identical to what you do in 250 with ands and ors. So that's a way to prove expressions about sets. Functions, we talked about functions, it's a map from one set to another. Okay, and there's three classes of functions. There's injective functions, which are one-to-one, which basically say different things over here map to different things in your target space. Okay, so f of x equals x, that's injective. F of x equals absolute value of x is not injective, because 1 and minus 1 both map to positive 1. There's surjective, which means you're mapping onto every element over here. So x squared is not surjective because nothing maps to negative 1. But f of x equals negative x is because everything over here gets mapped to from something in your domain. And then there's bijective, which is both injective and surjective, one-to-one and onto. And bijective basically gives you some sort of one-to-one mapping between the elements of the sets. The bijection is what we need to match cardinality. So a one-to-one correspondence between elements. We talked about sequences and summations and recurrence relations. So for example, n factorial equals 1 if n equals 1, n times n minus 1 factorial if n is bigger than 1. That's a recurrence relation. And it ties into recursion and it ties into induction, which we're going to talk about shortly. And the classic example, the more classic example is Fibonacci numbers. And if there's a recurrence relation for this sequence of numbers Fn. We talked a little about summation. I think people were familiar with these. Or not. So it's a shorthand for saying.
I mean, I was just saying, I completely forgot that we talked about summations and scores.
We talked briefly about matrices, basically, right, an n by m collection of things. You add them element by element, you subtract element by element, you can multiply this by some constant element by element, but if you want to multiply two matrices, you have to do some more work. So you do this row times this column, that gives you the upper left element, and so on. I'm probably not going to ask you to do that. And there's inverses for some matrices. So there's a one matrix, which we call the identity. And if you multiply by the identity, it doesn't change anything. It just leaves the matrix as it was. So there are sometimes for a matrix A, there's an inverse matrix, which when you multiply, you get the identity. That's what you look for when you're solving equations in 120, because if we have that inverse, we can solve simultaneous equations. And when you take linear algebra, or if you're taking linear algebra, that's where you get into all the details of that. All right, and then logic. So proposition is what?
Statement that's true or false.
It's a statement that's true or false, right? Pretty simple, but really, really important. So propositional variables are just letters usually that we use to represent a proposition. So P could be the proposition that it's raining outside. And it's a statement and it's either true or false. We can generate propositions from other propositions by doing things like negating P, saying P and Q, saying P or not Q, and so on and so forth. Each of those is a proposition derived from other propositions. We can also do propositions like this, if P then Q, and that's a proposition. It says nothing about whether P is true or whether Q is true. It's a simple statement that's either true or false. If it's raining, then apples taste good. Doesn't have to make logical sense. That's a statement and it has a truth value. But what we can say is that if we have a proposition like this, if it's raining, then apples taste good, And if we also know that it's raining, we can conclude that apples taste good. So we can start deriving statements from these
We know Q, provided that the first thing is true.
provided the first thing is true, provided that this is true, and provided that this is true.
But logically speaking, it has no bearing on what the actual content of P then Q is.
Correct.
Yeah.
Right, so it could be totally ridiculous, like if it's raining, then the sky is purple. Well, that might be true. I have to check today.
Purple isn't that exotic.
Yeah,
Sky is green.
zebra stripe.
There we go.
Green
That's
zebra
good.
stripe.
Gotta go for texture.
Yeah, so we have these conditional statements, and we can start doing logic on those. So we have these things like modus tollens, modus ponens, and so on and so forth, that let us derive propositions from other propositions. So, so this is absolutely true. And this has also got to be true. If P is true, then Q is true, but we know that Q is not true. There's no way that P can be true. Right? If you show up for the final, then you'll pass the class. And you don't pass the class, you can't have shown up for the final. Because this says if you show up for the final, you will pass the class. So the only way that this and this can both be true is if P was false.
That's true for this class, right? We'll show
Yeah.
up and get
Just
paid.
show up
what
and
a
put your
world
name
that
down.
is.
I mean,
Walk in.
doesn't necessarily make sense because you could conceivably not show up for a final and still pass the class.
But it makes sense in that world.
But if this proposition is true, right?
If you show up for the final, you pass the class.
Yeah.
Yeah.
But if you don't pass the class, that doesn't mean you didn't show up for the final. You could have failed the
But
final.
in that
true.
case, it does.
Right, so if you show up for the final, you pass the class. And you pass the class. Do we know that you showed up for the final? No. Right, it's possible that you passed the class because you got an A on everything else. Right. So if P then Q, and Q does not imply that P has to be true. So that's a fallacy. That's the fallacy of affirming the conclusion.
And that's what I'm saying. It sounds like you're doing over there.
But that thing is, they're not Q and P to Q are both true. We know they're both true. And the top one can't be true if not Q.
Yeah.
So like, you can't, well, if P not Q is true, and not P, and not Q is true, and not P is not true, I mean,
Yeah.
and P is true, I mean,
Right.
so that's a contradiction, which
Yeah.
doesn't work.
Whatever.
So if this is true, and this is also true, and suppose P is also true, we already know that P implies Q, and P tells us that Q must be true. And so now we've got Q and not Q both true. That's
What
a
if it's,
contradiction. That's what you just said.
Yeah, much better.
What if it's if and only if?
If and only if is,
I mean, like if Q is true only when P is true,
mhm.
but that's not a fallacy because Q can only be true if P is true.
This one?
Yeah.
Yes, so if this is P if and only if Q, and we know Q, then we can conclude P,
Okay.
Right.
right? Because separately we know Q implies P, and we have Q, therefore P, that's just this.
I guess I'm just hinging on the specific example you use.
Okay,
Yeah, just don't think about the example, because you're using real logic when we're talking about propositional ones.
so let's,
Yeah, it seems to work in propositions, but as soon as you try to add something to it,
all right, so,
That's just the example.
I think
is-
it's just.
You're
trying to
assuming
wrap-
things about the example based
Yeah.
on knowledge of the real world.
I mean, if you.
Right, so if you're a
the
dog,
only one has the consequence,
you like
that-
bacon, and you don't like bacon.
Doesn't mean you're not a dog.
You gotta be a dog. I mean, you can't be a dog. If you're a dog, you like bacon. Every dog likes bacon. You're taking that as a fact, right? That's what that first statement says. It says, if you're a dog, you like bacon.
Oh.
So it says if you're a dog, you like bacon, and it also says if you don't like bacon,
Right,
you aren't a
okay,
dog.
that works better.
Okay.
Yeah, there we go.
You always gotta do dogs. Okay.
You
I
can't
think
find it.
that's what you used on the exam when
Yeah.
we covered this. And,
Yeah.
yeah.
You can't find a dog that doesn't like bacon.
Mhm.
You should be your dog. He's helping a lot.
I know, I tell him that he's like on here. I told Marky he was on the quiz. So there's identities that go along with propositions, just like there's identities for sets and there's identities for Boolean things. So proposition and true is just a proposition. Proposition or true is always true. P and Q is the same as Q and P, and so on and so forth. Associative, commutative, distributive, there's a De Morgan's, and so on and so forth, and it's a strict analog to sets, and it's a strict analog to Boolean algebra. And so you can do the same thing we do with Boolean stuff and with sets. We can apply these propositions to transform statements into other statements and to verify them. We didn't do a whole lot of that, though. It's more working with these propositions. So this is one fallacy. The other fallacy we talked about was denying the hypothesis. So if P then Q, but P is not true, can we conclude Q is not true? And that's not a valid argument. That's the fallacy of denying the hypothesis. So if you're a dog, you like bacon, but you're not a dog, can we conclude you don't like bacon?
That was the connection I was making with the test.
Okay. So if you take the final, you'll pass the course.
But if you don't take
You
the
didn't
final,
take the final, but you might still pass the course.
That's what I was making the connection of.
Okay.
That's what it was.
Cool.
Yeah, but these are happening like in a vacuum, you know? Like,
Yeah.
No,
yeah.
I mean, yeah, this is what I was making the connection of. I was parsing it wrong.
Gotcha.
Okay, cool. And we talked about quantifiers. So universal quantifier for all x, existential quantifier, there exists an x. So we can say for all x, 2x equals x plus x. There exists an x such that 2x equals x. In particular, x equals 0.
Or one, or not one.
I think that's the only case.
No, just 0.
But for all x, we know that this is true. And we can do things like for all x, I would say for all x, where x is an integer, p of x is true. And that basically means p of 0, and p of 1, and p of negative 1, and p of negative 2. Alright, so they're just shorthands for wrapping our hands around big things. Alright, so modus ponens, and one more. Yeah, modus ponens, modus tollens, so, which is also argument by contradiction. So there's other things, there's hypothetical syllogisms and disjunctive syllogisms, and there's 2 pages from the book that I always refer you to, pages 58 and 59. Indirect reasoning, conjunctive simplification, etc., etc. And they just bottle these things together. But one you definitely want to be comfortable with is contrapositive. So this is always true, right? That's the contrapositive. these are not necessarily true. And I will never remember which is which. But I will tell you shortly. Maybe not. Anyway, one's the converse, one is the inverse. I'm going to guess this is the inverse, this is the converse, but don't quote me. I won't ask you. But these are both not, they don't follow logically. Okay, but this one does. This is the contrapositive.
And we're mainly using the contrapositive to change things around for proof purposes, right?
Yeah, and it's really just modus tollens,
Yeah.
right? P implies Q, not Q, therefore not P.
Right.
All right, so methods of proof. Right, a theorem is a statement that can be shown to be true. Methods of proof, there's direct and there's indirect. So a direct proof, you start with what you know and you work towards what you're trying to show. So 2 times an int is even. So I is an integer, 2I equals 2 times an int equals even. That's a really stupid proof. But
What's
there
the
you go.
definition of
Yeah.
an even number? Is it's 2k?
So that's a direct proof. Even plus even equals even, right? So 2I plus 2j equals 2 times I plus j, and that's an even number. That's a direct proof. Indirect proof, you take what you know and usually you try to find a contradiction.
Did you ever show us the prime numbers are infinite proof?
I think I did.
I can't remember if you did, because I know I mentioned it, and then a little while, you didn't cover it right then.
So that's a classic proof by contradiction, good example. Prove there's an infinite number of primes. So suppose number of primes is infinite, is finite. So there's only n primes, that's our assumption. So we can label them in order P1, P2, up through and including Pn. And so let Q equal the product plus 1. And so Q is congruent to 1 modulo P1. It's congruent to 1 modulo P2. It's congruent to 1 modulo Pn. So Q is not divisible by any prime, which means either Q is prime or Q is divisible by some other prime Pm, which is not in your set of primes.
Well, the first time I saw this done, I didn't see it done with modular arithmetic.
Yeah, well, we know modular arithmetic now, so it's easier.
Pretty much anything we know is fair game for solving
Yeah.
things in the final.
Yeah,
Well, proving things.
yeah, unless I say, don't do this. But I usually don't do that. Yeah, so both of those are contradictions. If Q is prime, it's bigger than Pn, and so this couldn't have been our whole set of primes. And if it's divisible by something other than these, then there must be a prime other than those, and that's a contradiction. So that's an indirect proof.
What was the difference between a constructive proof and a non-constructive proof?
There was a really cool example I found for that. Constructive proof actually, prove that there's a number with this quantity, and you actually come up with a number with that characteristic, right? Non-constructive one simply proves that there is such a number without telling you what that number is.
Okay.
And they're kind of slippery. I wish I could find that example because it was really fun.
So basically, with the non-constructive, you're saying this definitely exists. I have no idea what it is or how you get it, but it
Yeah.
exists.
Yeah.
Okay.
So prove that there's, right, so I could list 100 primes and say prove that there's another prime that's not in this set.
Right.
This proof doesn't tell me what that next prime is.
Right, so
It
yeah.
just tells me that there is another prime outside of that set,
So
but
this
it
is
doesn't actually
non-constructive
give.
because
So
you-
this is a non-constructive proof, yes.
You're saying there's an infinite number of primes, you're not showing how to get every
Yeah,
prime.
yeah,
Right,
exactly.
But,
I'm showing that
Yeah.
if you take any set of primes like this, there's a prime that's not in this set.
right.
But I'm not telling you how to find that prime.
Okay.
So that, yeah, thank you, that's exactly a non-constructive proof. So I don't know what to tell you about proofs. Like I say, they really just kind of come from practice and experience. But the general formula I think that I go through in my brain is take what you know and make sure you use it somehow. Right? Unless the person's throwing you red herrings, like there's a fact that you don't need. But barring that, you know, prove that the sum of 3 even numbers is, or 3 odd numbers is odd, right? Well, you've got to use 3 odd numbers somewhere. They're numbers and they're odd. What does it mean to be odd? Well, it's 2 times some integer plus 1, so write that down, right? This is 2n plus 1, this is 2m plus 1, this is 2p plus 1. And we're trying to show something about their sum. Let's add them together and see where that takes us. And you just start using what you know from the problem. That's kind of the first step. Make sure you incorporate all this information that's available, because presumably it's important. And then after you've put those down on your paper, right, and you've started doing whatever the problem is saying, the sum of these things or the set of these things or something, then you have to start looking at it differently and say, okay, what can I do to get from here to here? And there's always a bridge that has to be made somewhere. So I've got this expression for the sum of my 3 odd numbers. I'm trying to show that that sum is odd. Well, what does it mean to be odd? It means it's 2 times something plus 1. Okay, how do I get from this expression to this expression? That's the aha part. And that's the one that just kind of comes from staring at it. But if it's something that we've done in a few varieties already, and you've done it recently, those usually come pretty quickly. But at least the mechanics gets you most of the way there, right? Take what you're given, take what you're doing with what you're given, take what you're trying to get to, and then try to bridge that gap. Let's see.
Will we pick up the review tomorrow?
Yeah, we could. I really wanted to get through Turing machines tomorrow. But we should talk about number theory a little bit. And we should talk about induction and recursion, although I suspect most people are pretty up to speed on induction and recursion.
Yeah, it's not like we use prove every sense.
We should do a quick review on counting, but that was pretty recent, so pigeonholes, permutations, combinations. That takes us up to the previous test and homework. And then graphs and trees, I don't feel like we need to review, because we've been doing them recently, but certainly if you have questions, ask. And then formal languages, we'll try to continue with tomorrow. So what I'd like to get through tomorrow is those review topics, whatever questions you have, and then I want to at least mention Turing machines and get you to non-deterministic Turing machines, NP completeness, and the halting problem, because those are 3 really freaky takeaways to leave with.
You've got a lot on your plate tomorrow.
Yeah, I know. But we'll go as far as we can. We'll obviously spend most of our time on review as necessary, and then get into the freaky stuff.
Should we get like a stopwatch for you?
Yeah. Go. All right. I'll see you next time.